This is the GMAT 41. You are welcome to our basic inorganic chemistry class. In our previous class, we looked at development of atomic theory, different scientists that were involved in getting to discover atomic particles and with various experiments that they carried out. In this class, we introduced the topic origin of atomic spectrum. You would recall one of J.J. Thomson's experiments, the cathode ray tube experiment, where he discovered that cathode rays, when a gas is subjected to high potential difference and low pressure, it begins to emit rays, and then cathode rays move from the cathode to the anode, giving out light. Now, when we treated atomic model, we considered the concept of Bohr. Alright, there is Bohr, who suggested that atoms actually, when they are being excited, the electrons move from one energy level to another energy level, leaving traces of lines of characteristic frequency with wavelength, defining them, and that these electrons, they move with energy which is quantized, discrete, having specific values. Alright, now this whole idea gives rise to what we refer to as the spectrum. Is that okay? And so we start by asking the question, what is a spectrum? What is a spectrum? It is simply a collection of light of different frequencies or wavelengths. You know, the way this spectrum is produced is as a result of a beam of light. You know, a beam of light is a collection of lights being dispersed, being separated. When this light passes through a refracting surface, it could be like a prism. You know, for example, when you place a prism facing the sun, you would notice that this sun we see as white light has certain colors in them. Those colors are the component light that makes up this sunlight that we see. So when a beam of light is passed through a refracting surface, this refracting surface can disperse. You know, dispersion is a property of light, right? As a wave, to disperse it into its different colors of light. So this is actually how a spectrum of light is produced. What really leads to the formation of these lines, which gives rise to what we call the spectrum of light? When an atom is heated, or when you subject that atom to high potential difference and low pressure, or when you bombard the atom with an energetic particle, something happens to the atom. We refer to it as excitation. The atom becomes excited. Is that okay? The excitation is as a result of the atom having gained energy. And what is the consequence of this excitation? The electrons of the atoms will start moving. The electrons of the atoms will start moving. This idea we already established when we discussed the development of atomic theory. And when these electrons start moving, according to Niels Bohr, there are traces of lines they give. Is that okay? Now, these lines can be analyzed graphically using an instrument called the spectrograph. The wavelength of these lines, these traces of lines that the electrons give as they move from one energy level to another one, the wavelength can actually be depicted on a graph using an instrument known as a spectrograph. Niels Bohr stated first that the energy of this electron is quantized. They don't just keep moving with any amount of energy. No, it's discrete. That's the concept of quantized, with definite amounts. Finally, Max Planck carried out an experiment and then came up with his theory of radiation. Max Planck stated that the energy of one quantum of radiation or photon is an integral whole number which is given as NHF. That HF is a photon. That H there is Planck's constant, just like we encountered in the previous class. The F there is the frequency of the radiation of the light. According to Planck's theory of radiation, and following what Niels Bohr also stated, These electrons, their energy is discrete, is quantized, having whole number values. Maybe something like energy E of the photon, equal to 1 hf, which is equal to hf as you see it here, or 2 hf or 3 hf. He suggested that when the electrons are moving, from one energy level to another energy level, the amount of energy they either radiate, giving off, or they absorb, can never lie between a value of, say, maybe can never lie in a value of decimal. If you have something like 1 hf, 2 hf, 3 hf, you cannot have something like 2.1 hf, 2.5 hf, that would be a fraction, is that not so? Between two limits of whole numbers. That cannot be done. The amount of energy during radiation of an electron is quantized, is discrete, it has whole number. So that gives us this equation, and this equation is known as the Max Planck's theory of radiation. In the next video, we're going to see the properties that are characteristic of this light that is being radiated, and then we're going to treat the hydrogen spectrum specifically. Let us now give attention to the spectrum produced by a gas and that produced by a solid. Take note, we don't talk about the spectrum of liquid. Now, the spectrum produced by a gas is different from that of solid. For a gas, the spectrum produced is known as band or line spectra. A line spectrum is one that consists of well-defined light that has a well-defined frequency belonging to a particular line, wavelength belonging to that particular line, colors belonging to that particular line. There is no mix-up. Is that okay? So that's what a line spectrum is. It consists of a number of well-defined lines. These lines are called lights, that have specific frequency, wavelength, and what color. On the board here, I try to bring out this sketch. You can see how well defined and arranged these lines are. Is that okay? And that will help us to identify, okay, in the electromagnetic spectrum, we have what we call the electromagnetic spectrum, the jigsaw of Emery. Alright, that's just a name and it's an acronym I use to quickly remember how they are arranged in increasing order of wavelength. The gamma ray, the X-ray, the infrared, the ultraviolet, the visible light, and then the radio waves. Because a particular spectrum, when you're talking about atomic spectrum, can be found in a particular region of this electromagnetic radiation, which I just acronized as jigsaw of Emery. So when talking about line spectra, because they are well defined, we can actually easily identify them. Okay, this is the color of this light. This is the frequency, this is the wavelength. Okay, it is found in so region of the electromagnetic spectrum. We're going to consider that when we discuss the hydrogen spectrum next. Is that okay? All you need to know here is that a line spectrum, a band spectrum, is one that consists of lines of well-defined frequency having a particular wavelength as well as colors. A material emits radiation. The emission from a gas is known as the emission spectra. Emission spectra. And this actually helps us to identify a particular gas, because the emission spectra, or the emission from a given gas A, is different from the emission from another gas B. So this emission spectra serves as a fingerprint, fingerprint which you can use to identify a particular gas. Now let us consider the spectrum of a solid, because it's different from that of gas as mentioned earlier. Solids produce what we call continuous spectra. Continuous spectrum. And what is this continuous spectrum? A continuous spectrum is a spectrum that consists of light of all colors, wavelength, or frequency. So they are not defined. Just go in there, you see different kind of things, as if there is a mix-up. Is that okay? Now, I try to sketch out something to give the idea of a continuous spectra. If you compare this to that of line spectra, you can see the clear difference. Why this is well arranged, defined, continuous spectra is not. Please take note of this. When you have a continuous spectra that is produced from a solid and you pass it through a gas, if you pass it through a gas, something will happen. And what is that? You're going to observe certain dark lines. You're going to observe certain dark lines. These dark lines, will I use the word, is equal to or correspond to the normal lines that the gas would have emitted. Take note, when you pass a continuous spectrum through what? A gas, you will observe dark lines. These dark lines correspond to the normal line spectra that the gas could have given off on its own. These dark lines refer to it as absorption spectra. In the next video, we are now set to deal with the hydrogen spectrum, where we look at the well-defined lines contained in the hydrogen spectrum. The hydrogen spectrum. We want to look at how the hydrogen spectrum was discovered, developed. Of course, it's already an established fact that for an atom to be excited so as to make the electrons move, the atom will have to be subjected to a situation where their energy will be increased. You can do that either by bombarding it with an energetic particle or passing an electrical discharge through the gas or the atom at a higher potential difference and low pressure, or you can do that by heating. This was done to hydrogen, and when it was carried out, it was discovered that there were characteristic sharp lines of well-defined frequency, wavelength, and color. The first most important contribution to the hydrogen spectrum was put forward by a scientist in 1885 known as Johann Balmer. According to him, the wavelength of light in the visible region of the electromagnetic spectrum, that is talking about the line seen in the hydrogen spectrum. There is one of the line called the Balmer's series, the Balmer's line, which was seen in the visible region of the electromagnetic spectrum. Balmer proposed that the wavelength of that line can be calculated using his equation. And the Balmer's equation is given as lambda equal to b bracket n square all over n square minus n square, close your bracket, where this lambda is wavelength, the wavelength of the Balmer's line, of the Balmer's series in the hydrogen spectrum as seen in the visible region of the electromagnetic spectrum. Now, the value of n for Balmer's series is equal to 2. Because the truth is at the end of everything, there are 6 major lines that have been proposed by scientists which were found in the hydrogen spectrum. There are actually more than them, but the ones that have been discovered and pronounced, 6 of them. Balmer's series happens to be number 2. Actually, the first was Lyman, but before the discovery of that of Lyman, Balmer had first put forward this contribution. Is that okay? So his series was number 2 of the hydrogen spectrum, hence giving n equal to 2. N here represents other higher energy levels. Is that okay? So following what he said, if you put in n equal to 2, the equation will become this: that to get the wavelength of the Balmer's line in the hydrogen spectrum, which is found in the visible region of the electromagnetic spectrum, that lambda will be equal to b, which is the Balmer's constant, open bracket n square over n square minus 2 square. The value of the Balmer's constant b is equal to 3.6451 times 10 raised to the power minus 7 meters. Following this proposition by Johann Balmer, in 1888, another physicist by name Johannes Rydberg had to develop an equation that can be able to cover for calculating the wavelength of all other lines as seen in the hydrogen spectrum. Don't forget, I mentioned that there are 6 major lines or series that has been put forward for hydrogen spectrum. Is that not so? Balmer had already contributed to this first, focusing on his own spectrum, or his own line rather, or series in the hydrogen spectrum. So how do we account for other lines, for other series in the hydrogen spectrum? So Rydberg gave a generalized equation following that of Balmer, and he put forward the formula 1 over lambda, that is 1 over a wavelength, will be equal to 4 divided by Balmer's constant, bracket 1 over 2 square. He proposed for that of Balmer, where m is equal to 2. So it becomes 2 squared minus 1 over n squared, where n squared is other higher words series. Is that okay? For example, in the case of Balmer, that you have the value of 2. It means that n will start from 3, 4, 5 upward. We're going to discuss all of this in the next video, where we'll focus on the whole series as discovered in the hydrogen spectrum. Now, this 4 divided by B, he called it Rydberg constant. Is that okay? R. And all you need to do to get this Rydberg constant is dividing 4 by the Balmer's constant. So if you divide 4 by 3.6451 times 10 raised to the power minus 7, you're going to arrive at 1.0974 times 10 raised to the power minus 7 per meter, which happens to be the Rydberg constant. In the next video, we're going to write out the 6-fold series of the hydrogen spectrum and then write out the Rydberg-fold equation and see how we can use it to obtain the wavelength of any series in the hydrogen spectrum as well as the wave number. Then we are going to define the region of the electromagnetic spectrum where the series of the hydrogen are found. In this video, we now want to look at the hydrogen series, the spectrum of hydrogen, and the series that have been discovered and pointed out to us by scientists. We have 6 of them we are going to look at. 3 of them will be considered in this video. The rest 3 will be considered in the next video. It is important for us to know that all these series in the hydrogen spectrum, the wavelength and the wave numbers can be calculated using Rydberg equation. And this is the generalized Rydberg equation, which I've called equation alpha. 1 over the wavelength is equal to the wave number, V bar, we're using it for the wave number, and it's equal to Rydberg constant, whose value we already know. 1.0974 times 10 raised to the power minus 7 per meter. Open brackets, 1 over n1 square minus 1 over n2 square. Where n1 here is always the line, the position of the line you are dealing with in the hydrogen series. For example, when we considered Balmer, remember that Balmer was the second series. And so n1 in that case was equal to 2. Then we squared it. It is important for us to also take note of the region of the electromagnetic radiation where each of these lines, this series in the hydrogen spectrum, is seen. So let's do this. The first is the Lyman series. The Lyman series is found in the ultraviolet region of the electromagnetic radiation. What is the Rydberg equation for it? So you can see N1 is equal to 1 because this is the first hydrogen spectral series in the hydrogen spectrum. Is that okay? The first line. So it's going to be 1 over lambda equal to the wave number equal to R, open bracket, 1 over 1 squared. So you take note that N1 is equal to what? 1. Then minus 1 over N2 squared. It's very important for us to know that if N1 is equal to 1, N2 can never be 0 and it can never be 1. The value of N2 will start from 2, 3, 4 and above. The second line is the Balmer series. The Balmer series, as mentioned earlier, is found in the visible region of the electromagnetic radiation. And then the Rydberg equation for calculating the wavelength and the wave number is given us R bracket 1 over 2 squared minus 1 over N2 squared. Take note now, we are talking about the second series, so N1 is equal to what? 2. Which means that N2 will take values from 3, 4, 5, 6 going up. Is that okay? N2 can never assume the values 0 or 1 or 2. It cannot, because already N1 is already 2. Now, the next is the Paschen series, which is found in the infrared region. Infrared region is IR for short, because IR is infrared. Is that okay? Region of the electromagnetic radiation. The Rydberg equation is seen on the board here. R, open bracket, 1 over 3 squared minus 1 over N2 squared. Take note that in calculating the wavelength or the wave numbers, the case might be N1 for Paschen series is equal to 3, because this is the third series in the hydrogen spectrum, which means that the value of N2 will start from where? 4, 5, 6 upward. It can never, N2 can never be 0, it can never be 1, 2, or 3. In the next video, we're going to consider the remaining 3 series in the hydrogen spectrum. Now we want to look at the last 3 series in the hydrogen spectrum. So we have number 4, having treated the first 3 in previous video. The next is bracket series. Bracket series is found in the infrared region of the electromagnetic radiation. This is the Rydberg equation for bracket series. You notice that N1 is equal to what? 4, which means that N2 will take the value from 5, 6, 7 and above. N2 can never take the value from 0 to what? To 4. It cannot. Okay, now the fifth series is the Thorn series. The Thorn series. It is found in the infrared region of the electromagnetic radiation. Once again, the Rydberg equation is giving us this for calculating the wavelength of the series as well as the wave number. N1 in that case is 5. So you have it as 1 over wavelength equal to the wave number equal to Rydberg constant bracket 1 all over 5 square minus 1 over N2 square. Now if N1 is equal to 5, simply means that the value of N2 will take its value from 6 and above. Is that okay? N2 can never assume the value from 0 to 5. The last series here is Humphrey's series, discovered in 1953 by C.J. Humphrey. It is found in the infrared region, but this time in the far end of infrared region. Is that okay? In the far infrared region of the electromagnetic radiation. What is the Rydberg equation for the Humphrey series of the hydrogen spectrum? It's giving us 1 over the wavelength equal to the wave number of the series equal to the Rydberg constant open bracket 1 over 6 square minus 1 over N2 square. So you see that N1 in that case takes the value 6. It simply means that N2 will now assume value from 7 and above. N2 can never take the value from 0 to 6, 0, 1, 2, 3 down to 6. It cannot. Now we are done with the various series, 6 of them in the hydrogen spectrum. 5 is more pronounced, stopping at this form. Is that okay? In some cases, you may just not encounter this Humphrey series, so take note. However, you should know that that series has also been discovered. Now, on the board here, I have a memory aid acronym that can help you learn this series because you are expected to know them serially the way they were presented in the video here, so that the N1 value would not be a challenge to you. Remember, the first is what? Lyman, the second is the Balmer, the third is Paschen, the fourth is brackets, the fifth is found, and the sixth is what? Humphrey. So what's the acronym? We have the LBP-BPH, which I chose to call low blood pressure, high. Low blood pressure, high. I hope you can remember that. It's just to help you memorize the arrangement. We have the first low here is Lyman. The second, we have B, blood for what? Balmer. We have P, pressure for Paschen. The next B, blood, represent brackets. Then the next P is found. And then we have our H, which is high, representing Humphrey series. In the next video, we shall look at the relationship between the speed of light, the wavelength of these series, as well as the frequency. And we're going to look at how this can be related to the energy change, the photon, when an electron jumps from one energy level to another energy level. After which, we'll look at calculation for this topic. In this video, we want to look at the relationship between the speed of light, the frequency, and the wavelength of radiation. It's a known fact, as we've explained previously and severally, that when atoms are excited, their electrons move from one energy level to another. So once this happens, there is this relationship between the frequency, wavelength, and speed of light. It has been found that the product of wavelength and the frequency of a given radiation is equal to the speed of light, which is 3 times 10 raised to the power 8 meters per second. So this is the point here. The product of frequency and speed of light or radiation is equal to a constant known as the speed of light. So please take note, the speed of light C is equal to 3 times 10 raised to the power 8 meters per second. That's the value of the speed of light. So this relationship, F times lambda, frequency times wavelength, is equal to C. If you make frequency subject of formula, you see the formula to be the speed of light divided by what? Lambda. You can also choose to make lambda wavelength subject of formula, you get speed of light divided by what? Frequency. Now let us consider the energy level of an atom and then see how we can relate the frequency or the speed of light and wavelength to the energy of a photon when there is a quantum jump of an electron. Imagine an electron moves from one energy level to another one. what's going to be the value of the photon. So we want to find out. On the board here you have a sketch, okay, just use it to show different energy level. The lowest level here called the ground state, where we say that the atom is stable because we've not excited it. We refer to it as the ground state. So you see the energy level E0. So giving quantum number 1 there, is that okay? Now when an electron moves, let's say from this to this particular level, it's possible for us to calculate the energy that the electron, alright, that's the photon. When I talk about photon, it's like packet of light, still referring to energy, is that okay? Now, if there is a quantum jump from this E0 to E1, we can actually calculate the photon that has been radiated by doing E1 minus E0, which will now give us a generalized formula here that change in E is equal to En minus E0, which is equal to HF. We've made this before. This N represents the given higher energy level. Is that okay? Then, and we already established that F is equal to speed of light divided by lambda, so that this formula can still be written as H, the Planck's constant. Then in place of this frequency, you put speed of light divided by what? Lambda of that higher frequency, of that higher energy level rather. So this equation 3 is very important. Now, just like we learned for the hydrogen spectrum where we talk about the different series, if we're able to calculate the wavelength, we can actually determine the what? The frequency using this formula. And once we get the frequency, we can calculate the energy. We can calculate the energy of any electron moving from a particular series to another series using equation 3. So that is how important these equations are. Take note, there can always be a quantum jump from any given energy level to another one. Like this now is from the ground state to E3, is that okay? And then we can also have the jump, let's say from E2 to E4, it's possible. Where you can now do E4 minus E2 as the case might be. Take note that the ground state of an atom is the least energy level, and we refer to it as an atom which is closest to the nucleus. Once the electron is excited to the highest point where you have energy of infinity given as 0, that is at ionization. In that case, the energy level is equal to what? 0. In the next video, we are now set to pick questions and solve. In this video, let us now look at how we can count the lines of any given hydrogen series. You will recall that in the previous videos, we've already established that there are 6 major sets of hydrogen series that have been identified in the hydrogen spectrum. We mentioned the Lyman being number 1, the Balmer number 2, the Paschen number 3, the Brackett number 4, the Fond number 5, and then the Humphrey number 6. I stated that it's very, very important that we know the arrangement of this series and then have them at heart, because the arrangement, as I just mentioned, represents their ground state. The serial number there represents their ground state. So Lyman is number 1, meaning that the quantum level in the ground state N1 will be equal to 1. And then Balmer is 2. The ground state quantum level N1 will be equal to 2. Humphrey is number what? 6. So the ground state quantum level N1 will be equal to what? 6 in that case. Now for us to determine the higher quantum level N2, it's very important for us to know how to count the lines, is that okay, in a given series. And that is what we actually have on the board here. But before we proceed, I'd like to state that we have the ground state of any atom. And of course, the ground state we refer to it as the most stable state. At that point, the electrons do not exhibit quantum jump, is that okay? And once there is no emission, at that ground state, no emission, it means that we do not expect to see any line in that case. Now, once the electrons are being emitted, what do we expect to see? Lines will start being produced. So if you come to a particular series, the line that is being produced in that series is counted as first, second, third line down to infinity, as the case might be. Now the ground state, because there is no emission at that point, I decided to call it line number 0. Is that okay? The ground state. Now, after that, the next line is taken as the first line. And like that, we have the second line, the third line, the fourth line, the fifth line, down to what? Infinity. Now, all these first, second, third, and fourth lines like that represent the higher quantum levels in terms of the line. of a given series in the hydrogen spectrum. For example, let us assume that you're asked to calculate the wavelength or the wave number or the frequency or the energy in the third line of, let's say, bracket series. The third line of bracket series. How do we go about that? Remember the right-back equation. We have it that 1 over wavelength is equal to the wave number, which is equal to the right-back constant, times 1 over n1 squared minus 1 over n2 squared. Our problem is how to determine n2. Is that okay? So let's come back to this now. As an example, you are to determine a particular value or quantity in the third line of bracket series. How do you go about that? Remember, the ground state of bracket series is what? 4. Because the bracket series in the hydrogen spectrum is number 4. Which means that N1 in that case will be equal to what? 4. The ground state. Now you have to calculate this quantity in the third line of bracket. So what will now be the N2 for that third line? The higher energy level in that case, based on the question you are being asked. So this is what you will do. Remember the ground state for bracket series, N1 is equal to what? 4. So the third line now you have to draw 1, 2, 3 lines above the ground state line. Is that okay? So that will take us to this point, the third line. So what do you do to get your N2? Remember, N1 for bracket now is equal to what? 4. So the first line begins with the value of N2, any higher quantum level. So the first line will now be N2 equal to what? 5. If it is second line you are doing calculation based on, N2 will be equal to what? 6 for the bracket series. Now, our problem is based on the third line. So you take note that on the third line, in bracket series, N2 will be equal to what? 7. Which means that in the right back equation, your formula, the bracket side is going to be 1 over N1 squared minus 1 over N2 squared. For bracket series, N1 is equal to 4. So it will be 1 over 4 squared minus 1 over. Now we calculated something for the third line. The third line, N2, is equal to 7 for bracket series. So it will be minus 1 over 7 squared. I hope it makes sense. Quickly, let us look at what if you're calculating, let's say for fund series. You're meant to calculate the value of a quantity, maybe wavelength, wave number, energy or frequency in the fifth line of fund series. What do? The ground state of fund is what? 5. Which means that N1 for the fund series will be equal to what? 5. Now what's going to be the N2 since you are calculating for the fifth line? So again, you locate your ground state where N1 for fund is equal to what? 5. Then you now draw 5 lines above it because you are calculating for what? The fifth line. So above the ground state you have 1, 2, 3, 4, 5. Then you check what N2 is going to be for the fifth line in the fund series. Coming here now, let's look at it. N1 in the fund series will be equal to 5. Is that answer? So if it is 5, it means that N2 value will start from 6 above. So you come in the first line, N2 will be equal to what? 6. The second line, N2 will be equal to 7. Third line, which will be equal to 8. Fourth line, which will be equal to 9. The fifth line now, the N2 value will be equal to what? 10. So you go back to the right back equation. Then the bracket side of that right back will be 1 over N1 squared. N1, the ground state for fund, is 5. You fix it 5 squared. Then minus 1 over the N2 for the fifth line that the question is based on is 10. So it will be 1 over 10 all squared. So take note of that. Please, I want to state this quickly. The right back constant is 1.0974 times 10 raised to power 7. Positive 7, not minus 7. Is that okay? Positive 7. Take note of that. Then per meter as the unit. In the previous video, we considered a situation where an electron jumps from, let's say, a ground state of a particular hydrogen series to any higher energy level in that same series. Where in such a case, the line where it jumped to is being specified, jumping from the ground state. Well, so in such a case, we have to count the position of the line to help us determine the higher quantum number level, N2. Take note, the jump is exhibited in a particular series. In this video, I want to consider a situation where this electron now moves from one series to a different series entirely. Just imagine when a quantum jump is from Balmer's series to Humphrey's series, or from Lyman's series to Paschin's series. Or you talk about the jump from Lyman's series to bracket series. How do you handle such situation? In this case, there is no specification of the line where the electron jumped from and where it jumped to. The position of the line where it jumped to in the new series. Nothing is being mentioned like that. How do you calculate possibly the wavelength, the wave number, the frequency, the energy, as the case might be, for such situation? And the body will have this short note. Very importantly, this part that's waiting with blue and red marker. When there is a quantum jump from one energy level or one hydrogen series to a different hydrogen series, N1 in Rydberg's equation is taken as the value of the ground state of the lower hydrogen series, and then N2 is taken as the value of the ground state of the higher hydrogen series. That's how you handle that. Take note, there is no specification of the line it jumped from and the line it jumped to. Not specified. So in that case, you use the ground state of the two different series for your calculation. An example is given here on the board. We look at a case where an electron jumped from Balmer's series to Humphrey's series. So if we come to Rydberg equation, 1 all over lambda equal to wave number equal to the Rydberg constant, open bracket, 1 over n1 squared minus 1 over n2 squared. What's going to be your n1? What's going to be your n2 in this case? So you have it here. The Balmer series is the lower hydrogen series compared to what the Humphrey's series. So n1 in that equation will be taken as the ground state value of Balmer's series. And ground state value of Balmer series, you know, is equal to 2. Is that not so? We've discussed that in the previous video. So our n1 will be equal to 2. When we want to do the calculation, you can see that. Then the n2 will be taken as the ground state of the higher hydrogen series. In this case, Humphrey. What's the ground state of Humphrey? You still remember that? That's correct. The ground state of Humphrey is n1 equal to 6. Now in this case, in that Rydberg equation, our n2 will now become the n1 value of Humphrey. You can see where I wrote n2 equal to what? 6. So that's how we handle that situation. Now, having considered the electron quantum jump in two different cases. One, when the jump is within the same series. And two, when the jump is between two different series. I want to state at this point, please, under this note, we have a powerful point here. Whenever in a given problem, the position of the line it jumped from and the position of the line it jumped to is being specified, whether this quantum jump is exhibited in one particular series or whether the quantum jump is between two different series. Once the position of the lines are mentioned, please, it's very important that you do line counting. It's very important that you do what? Line counting. So you sketch the lines and then you count, just like I did in the previous video. That will help you to get your n2 value. Just imagine, maybe if the jump is from, let's say, the second line of any series to maybe the fifth line of that series. You know, second line to fifth line, it means that n1 will now be the value of that second line. And then n2 will be the value of what? That fifth line. So, sketching and doing your line counting will save you in such case. It is now time. We are ready to pick questions and solve, applying all these formulas that are being established under hydrogen spectrum.